Hello, good evening, welcome one and all. And I would wholeheartedly like to welcome the participants that have joined the session just now. So today we are towards the second half of the program wherein we are at the most interesting phase of the sessions that would be conducted now on. And we talk about the emerging trends in dairy refrigeration and pressure vessel design. Today we have Mr. Sudhir Kumar, who is one of the renowned practitioners in this area, and he would be discussing with us about the same. Mr. Sudhir Kumar is the Director of Marketing for Flick India Limited, and he holds more than 30 years of experience. He is an MTech from IIT Delhi, and he has experience in industrial refrigeration and air conditioning. He is the past president and founder member of Association of Ammonia Refrigeration. He is a regular presenter for Bureau of Energy Efficiency, AAR, NHP, and Confederation of Indian Industries on energy efficiency for refrigeration system. He is also a member of the Confederation of Indian Industries South Region Agriculture and Food Processing Subcommittee. Sir, over to you. Welcome, sir. Your audience.
Good evening. Good evening to all. Thank you, Shruti, for a wonderful explanation about my profile.
Now, so we would be taking a little bit of insights from your experience for our audience today.
Yeah, thank you. Thank you, ISHRE and REFCOLD organizing committee for inviting me to participate or give a small presentation on emerging trends in dairy refrigeration. And it is in the evening today, and you have been attending a lot of seminars. I will try to make this presentation as interesting for you. And over the years, I have been working on dairy refrigeration field. So I would like to share some of my experiences on what are the emerging trends. First, before going into the core of my presentation, I would like to just give you a small idea about how the process of milk collection takes place. First, milk is milked and it is going to the small farms, and the small farms, it goes to the rural milk collection center, and from milk collection center it is cooled, and then after cooled or chilled, the milk is then transferred to bigger dairy projects, dairy plants in reefer vehicles or in insulated vehicles. And from there, it is processed in the milk processing plant where it is packaged, made into various other byproducts like cheese, butter, etc. And then after that, kept in the cold storage and then passed on to the various markets where the consumers consume the milk and milk products. This is the collection point where the milk is collected, and after the milk is collected, it is going into a bulk milk cooler or a chiller. Basically, milk comes at around 35 degrees in warm climates, and sometimes it comes at 30 degrees. It has to be cooled as early as possible. Maybe within 2 hours, you have to cool it to 4 degrees or maybe even at least to 8 degrees, and then take it to the main processing center. This is a typical layout of a rural milk collection center where the milk is received and processed, where you will have a small refrigeration plant. Either it is in bulk milk coolers or a small PHE system where you can cool milk up to 5,000 liters or 10,000 liters per day. It's a typical layout. And these are basically located at small village levels or at the district headquarters levels. And from there, the milk is then processed and then taken to the bigger dairies, which are located at least 100 kilometers or maybe 200 kilometers away from the rural milk centers. This is some of the processing happening. The main process This is a big layout which I will not go into the details of it, but basically after the milk comes into a dairy, first it is again chilled. Even though the milk comes chilled, it is again chilled in the milk processing center. After chilled, it is pasteurized. After pasteurized, it either goes for packing of milk as liquid milk, or it goes to the process where various byproducts are converted from milk. So this is a big layout of a typical big dairy project, where the total, you can find that the refrigeration plant is separated from the main complex, and refrigeration is from there, it is gone by chilled water or by ammonia directly. Now let us go and into the main presentation part. First, we will discuss on what are the main refrigeration load in dairies. There are two types of load. One is the indirect load, where we use chilled water for chilling of raw milk, tanker milk, and also pasteurization, and also buttermilk chiller, etc. Whereas the direct load is the direct ammonia or any other refrigerant goes into the cold rooms, butter cold rooms, or dahi cold rooms. So basically direct refrigeration and indirect refrigeration. The various process of indirect refrigeration is by using chilled water. We use chilled water at close to 0 degrees, either from a IBT system or from a PHE system. We give the chilled water to the various processes in the dairy. Basically raw milk chiller, where the milk is cooled from 34 degrees to 4 degrees. If it is a tanker milk chiller, then it is from 10 degrees to 4 degrees. Pasteurization of the milk happens. Basically, milk is heated up to 80 degrees, and after that, it is regenerated. And then after regeneration, we use chilled water, which is basically cooling it from 14 degrees to 4 degrees. Again, buttermilk also is cooled from 45 to 4 degrees, and aging tanks where we maintain the temperature at 4 degrees. So basically, to calculate this load, because you need to calculate the total load required per day. So you need to plot a histogram to design the optimum system and the base load of the system. How do you calculate a histogram? This is a typical histogram where you have the various timings, milk coming, and what all the process you are doing. Basically, like if you see here, the first process is a tanker milk chilling, then there is a buttermilk chilling, and the timing is also staggered, like in some places you will see the rinse milk is the milk which is stuck to the cans. Those are cleaned and they are also chilled to 4 degrees. So rinse milk chillers, it will be at a staggered timing. So once you know various process, this is a very important part in designing for a dairy plant. You need to know at what timing the milk is coming and what process you are doing, because if you start doing all the process at a time, then your peak refrigeration load becomes very higher. So it is better to stagger the loads, and based on the staggering of load, then you design your refrigeration plant. Once you know the total heat load, once you plot it, then you can carry out the peak load, base load, etc. See, if you see this chart, this will explain you how it is. Like, see, at certain point of time, the load goes up to 500 TR, and certain point of time, there is no load, literally no load. It is coming to 0. And again, it increases. See, it's basically the process. In the morning, it is more. Again, in the evening or in the late night, the milk is collected, and at the time, the refrigeration load is more. But in between, the refrigeration load is less. So after you design this, then we also have a different type of a histogram. Here, I have put various colors for the various processes, so that we call it a skyscraper. So you can know that the same drawing which we saw earlier is the same here also. Once you arrive at this, then we arrive at a base load. See, what is the base load is a constant load. At any point of time, a constant 150 TR is required majority. So that is called the base load, and this peak load is taken out from the latent heat, which is the IBT system or ice silo system. So you need to plot this histogram in order to come to the optimum capacities of the refrigeration plant. The other heat load is the refrigeration load of the direct heat load. The direct heat load is basically a milk cold room, or it can be a butter deep freeze, or it can be an ice cream deep freeze. So you need to have the various parameters, like what is the ambient temperature, what is the door opening, and what is the incoming temperature, product load, what is the incoming temperature, and supplementary load or miscellaneous load is the number of fans, number of people working. So this is how we calculate the heat load for the direct load. So once you calculate both the loads, the indirect load and the direct load, then we can design a refrigeration plant. This is one of processing of milk byproduct, just a slide. I've just given you a flow chart. You can see here, once the raw milk is come, it is pasteurized, it goes to cheese vat, or it goes to a curd formation, or after cheese some whey is drained. So it's the process flow, where all we need the chilling. See, pasteurization, after pasteurization, we need cooling. And again, in curd formation, we have to use blast freezer to cool the curd. Similarly, this is for butter and cream also. You will need cooling at aging tanks, cooling of the cream. Everywhere you need cooling, which is used by chilled water. And then afterwards, the storage is at minus 23 degrees, which is using direct refrigeration system. Similarly, for curd, this is the curd process. And this is a typical cold storage of milk cold room, which is fully packed up. And here it is of a butter cold storage. So you have butter cold room, which is stored at minus 23 degrees or minus 20 degrees. Milk cold rooms are at 3 to 4 degrees. So milk cold rooms are stored at 3 to 4 degrees. This is again one of butter storage. And this is a milk cold storage, to just give you an idea. Okay, now we come for the types of chilled water generation. What are the types of chilled water generation? There are 3 types of chilled water generation. One is the conventional IBT system. In the earlier days, the dairy plant used to have only IBT system. And this IBT system used to work at minus 10 degrees, and it was a very foolproof system. People used to have IBT system so that in case if there is a power cut or you have a power failure, also you have ice stored in your ice bank tank. Then after some time, they found that ice bank tank was not energy efficient because it was running at a lower suction temperature. So people started designing a IBT plus pre-chiller system. So basically, there will be an IBT, but the peak load is cooled by the pre-chiller system. Say, for example, after cooling off the milk in the process area, the water gets heated up. It comes at say 11 degrees or 12 degrees. Once the 11 degree, 12 degree water passes through a pre-chiller, it is cooled up to 4 degrees. Then the 4 degree water goes into the IBT system. So in this way, you can reduce the size of the IBT and use a PHE for the pre-chiller system. There is also, instead of PHE, people are now using falling film chiller also. And then the next system is, you can use a direct PHE chiller. In some chilling centers, they don't go for IBT system. They only use chilled water PHE system. Or you can use a glycol for deep chilling. If the milk has to go to longer duration, then you cool it even lesser temperature using glycol system. The major advantage of an IBT system is the thermal storage is available. Like say in some places, if there is a differential power tariff, in the nights the power is less, then this IBT system becomes more relevant. And also the design of the system becomes smaller because you divide the total plant load by 20 hours of operation, and then the refrigeration plant capacity becomes smaller. And similarly, these are safe during power cuts and breakdowns, which I explained to you earlier also. Then the other aspect comes is when you are designing the cold rooms. In what ways you can save the energy? The first and foremost point in a cold room is you have to be very careful about designing the height of the cold room. Like if you build a cold room for 5 meters height, milk is stored only up to 6 feet. That is approximately, it's only approximately 2 meters. So in no point in building a cold room with 5 meters. So it is optimum should be around 3.5 or 4 meters in length. And similarly, definitely negative temperature cold rooms should have anti-rooms. And also the air cooling design with a proper temperature difference must be selected. And the drain pan should have heaters, and heat tracing also should be available in the drain pipes. And proper hot gas defrosting controls are required. Apart from that, you need to have air curtains, sliding doors, and also strip curtains to save on the energy, because the purpose of using an air curtain or a strip curtain or a sliding door is to avoid the loss of temperature from the colder area to the hotter area. And the next concept which we were talking is like using only IBT, instead of IBT, using only a PHE with a small tank instead of using an IBT. You can use falling film chiller with the IBT system, and also another one system is without IBT system, just have a falling film chiller or a PHE and then collect the water in a tank and use this water for your process. The most energy efficient system will be this one, because it operates at -2 evaporation, and by using at -2 evaporation, your power saving is definitely better than an ice bank tank system. I have made some small calculation. Say for example, if it is a 1 lakh liter dairy, 60,000 liters of milk will come in the morning and 40,000 comes in the evening. So by using this system, you are able to save lot of power, but definitely there is one disadvantage is you will have a bigger refrigeration plant. So I've made a small comparison. This is an actual comparison which we have made. It's calculated based on the theoretical loads and from the rating charts we have taken. So you will find that if you run a system at -2 degrees, the BKW per TR will be only 0.75. Whereas if you are running a system at -10 degrees suction, then the power consumption will be at 1 kilowatt. So if you compare this, you are approximately saving 25 to 30% of power. Yes, straight away we are saving 25 to 30% of power. But as I told you earlier, it is better to have a combination of PHE with a small IVT system. Next comes the heart of the refrigeration system. So first we have selected what is the system configuration. After that we go in for a compressors, which are the heart and which is the major power guzzler. So basically in a refrigeration plant, the major power is consumed by the compressors. So small for chilling centers and small dairies, people can use reciprocating compressors ranging from 20 TR or rather 60 kilowatt to almost 100, I would say 100 TR, even though it's mentioned 150. 100 TR is approximately about 350 kilowatt of refrigeration capacity. And also you can have two-stage systems. If you are having a small butter deep freeze, then you can use a small reciprocating compressor. Then the latest trends are rotary screw compressors, twin screw compressors, which ranges from a capacity of say 100 TR to 1000 TR. We have nowadays dairy projects which are going up to 2000 TR in a single dairy project. So if you're going for a bigger project of 2000 TR, which is approximately 7000 kilowatt refrigeration, then it is not possible to go in with a reciprocating compressors package. It is better to go in for a bigger compressors. So we start using screw compressors. So screw compressors got various advantages. One is it's got fewer moving parts, and plus it is running at a very high RPM, which is approximately 3000, 3500 RPM. So the capacity, for the same capacity, the plant room size becomes smaller. And also, this is how a compression works in a screw compressor. Between the male and female rotor, the gas, the red color one, which is shown in the slides, is how the gas is compressed from the suction to the discharge. So it is directly coupled to the motor running at approximately 3000 RPM. So once the major advantage of a screw compressor is you save on the plant room space, plus the automation of the controls, and the capacity control mechanism is very good in a screw compressor, where you can operate it at 10% also. And also you can use a VFD drive. Of course, there will be a slight power penalty if you are not using, if you are using a capacity control and running a plant at 50%. Definitely there will be a power penalty. So the system must be optimally designed in such a way that you have multiple compressors based on your capacity. So once you select your compressor, the energy saving happens in the compressor part. Next comes the motor selection. Nowadays, a lot of motor efficiencies. We are seeing EFF1 and EFF2 earlier days. Now the motor efficiencies are now being classified as IE2, IE3, and even IE4. The latest generation motors are IE4, whereby you save power and the payback period is approximately 2 to 3 years if you use a IE3 or IE4 motors. The difference between IE3 and IE4 is not much, but you will definitely find a power saving between IE1 and an IE3 or IE4 motors. These are some of the efficiency curves which are used for the motors. I have just given you a small comparison for a 200 kilowatt motor. If you see, IE1 is about 0.94, whereas IE2 is 0.95 and IE3 is about 0.96. So you will be saving power of about 2 lakh rupees per year. So definitely using an IE3 motor, even in your existing plant, if you are an old plant and if the motor is already rewound 3 times or 3 times, it is better because the efficiency is down if you are rewinding the compressor motors. So it is better to shift to a new motors. After coming to compressor, then we have discussed about motors. The next major part where you can save on power is the VFD. VFD is nothing but a variable frequency drive, where you are able to control the speed of the motor to reduce the capacity of the refrigeration system. So by using a slide valve, also you can reduce the capacity. But if you see in this chart below, you will find that at 75% slide valve position, capacity is at about 1.14 is the BKW per TR as compared to the 100% load of 1.03. Whereas in a VFD system, you can see by speed controlling, we can get the same capacity at approximately 1.06. So you are getting a difference. The more lower the slide valve position, the better you get in the power saving with a variable frequency drive. There are various manufacturers doing variable frequency drive, which is now the. And one more advantage by using a variable frequency drive is olden days we used to have star delta starters, which used to take a starting current, and then soft starter which used to take 1:4 times. So you can use a VFD. Of course, there is one small disadvantage using a VFD system. If you're using a VFD system, the major one expense which you will incur is you'll have to have a harmonic filter, because sometimes it will disturb the harmonics of your other equipment. So while designing a refrigeration plant with VFD drive, you should take care of harmonic filters also. Next comes, after we have seen in the compressor motor and the drive, And next comes the Desuperheater system. Desuperheater system is nothing but you use the discharge gas before going into the condenser is used to cool. It is used to cool hot, rather it is used to cool before the condenser. It will heat up your hot water requirement because dairy projects require a lot of hot water for floor cleaning, crate washing, and even for boiler preheat water. So you can take the waste heat from the compressor discharge, which is at 75 degrees or 80 degrees. Before going into the condenser, we use a heat exchanger. It can be a PHE or a plate, shell and plate type. You can use or a shell and tube. Use it to cool, heat the water to generate hot water. So by using this system, your condenser capacity also reduces. At the same time, you can get a lot of the COP of the plant increases because you are generating little amount of hot water in the plant. Next comes the evaporative condenser. The evaporative condensers are one of the better condensers in the modern field. Earlier days also we tried using evaporative condensers, but because of the water quality, availability was not good. People were not using evaporative condensers about 20 years back. But with the latest water treatment plants, industrial soft water being used, and people are now aware of the water management. So now evaporative condensers have come here to stay. They are one of the energy efficient ways of working in a refrigeration plant. A small illustration has been given, like using a evaporative condenser versus a cooling tower and PHE condenser. This, even though the calculation shows this is for a 300 TR plant, if you are having a 1000 TR plant, then definitely you will have a better advantage in using an evaporative condensers. Then comes the thermosiphon oil cooling, where you use the liquid from the receiver is used for cooling the oil. Normally we used to have water from the cooling tower to cool the oil, but that has two inbuilt disadvantages. One is if your water quality is bad, then you will be damaging your oil cooler and the oil cooler tubes will get leaked. And the other disadvantage is you are using a pump about maybe 5 HP for one oil cooler. And if you are having 5-6 oil coolers, then you will be consuming a lot of power for pumping water into the oil cooler. So basically, using a thermosiphon oil cooler, you don't need to use any pump. It flows by the gravity. Ammonia at 40 degrees cools your oil to 45 degrees. This is one of the better systems now which we are using. And after finishing off with evaporative condensers, the next important aspect is the ammonia pumping recirculation system. Again, this recirculation system has been used in dairy plants for more than 10-15 years, and they have found a lot of advantages in the system. The first and foremost advantage is superb refrigerant distribution. In olden days, you are expected to throttle the valve and expect to flood the coils. Whereas in this, it is all done automatically and it is pumped through. So basically, where you need to send 1 kg of ammonia, within the same time, you will be sending 1:4, that is 4 kg of ammonia. So your evaporator is completely flooded continuously and your heat transfer efficiency is better. And the major advantage of this is it will safeguard your compressors from liquid slugs. So that is also one of the tremendous advantage of this system. Next comes the air cooling units. Olden day refrigeration plants used to have air cooling units floor mounted, having a blower and having a ducting system. But now the latest air cooling units are all with stainless steel, aluminum fins and more energy efficient, using again IE3 and IE4 motors and all low noise, and also it is hygienic nowadays because all the dairy projects are all HACCP approved. So you need to have a hygienic coolers where you can have a SS casing or a powder coated casing. And this also gives you a lot of saving by using IE3 and IE4 motors. And after finishing off with the refrigeration system, you come into the chilled water side. Once you come to the chilled water side, you can use the energy efficient vertical inline pumps. Again, these are directly coupled pumps, and these are having a reduced horsepower as compared to the normal pumps. And also similarly, based on your load requirement, you can have a variable frequency drive even in the chilled water circuit, and by that you can manage your refrigeration system capacity also. Say for example, now at this point of time, you are only requiring 100 meter cube per hour and your pump is 150 meter cube per hour. You can use a variable frequency drive, reduce the speed, and only pass on 100 meter cube to your process. So indirectly, it again reduces your load in the PHE or IBT system, and your compressor unloads and saves power. So this is one of the very good developments in the chill water lines, where you will have vertical inline pumps and variable frequency drive. And next, not last but not the least, is the important factor of automation in dairy or any refrigeration plant. See, the first and foremost is your labor cost comes down, and you can monitor the data accurately, and the improvement in the efficiency of the plant is tremendous because you are having all controls which are monitored through a PLC or a SCADA system. You can use ultimate control systems, like you can have transmitters reduce the speed by the suction pressure reduction. So this is one of the biggest innovations in the dairy field. We have seen a lot of dairy projects now completely automatic operation, right from milk receipt to the outgoing also. So everything is completely captured in the SCADA system. In the SCADA system, you can see all the complete plant parameters, and also it can be operated from a single control disk. So you are avoiding lot of operators cost, and also you are saving on the energy efficiency because you are running the plant accurately, not dependent on the operator's efficiency. So this is one of the major innovations in the dairy system. You can have a data logging so that you can also calculate trends. Basically, like last year, what was your power for this much liters of milk? Say, if you're having a 10 lakh liter dairy, it can calculate in a graphical state that how much power you are consuming for per liter of milk. And by doing that, you will also have a trend. So say you can see after 1 week for the same milk, if there is any increase in power, then you know there is something wrong in your plant and you can check the efficiency. So you can have a trend system, MIS system, so that you will have the complete data logged in, and you can even get it in your mobile phones. The owner can see how much was the power consumption today. So some of the dairy installations with the latest energy equipment, you'll see the VFDs are placed next to the compressor itself, and the PLCs are also placed next to the compressors. So I would like to conclude because it's been a lengthy presentation. Thank you for patiently listening to my presentation. But the major conclusion I would like to say is use of screw compressors in a bigger dairy plants. I'm not against reciprocating compressors, but it is basically if you have a bigger refrigeration capacity, then you can use screw compressors. Otherwise, if it's a smaller plant, you can use reciprocating compressor also with variable frequency drive, with IE4 motor and PHE plus IBT system. You should have always a combination of PHE plus IBT, because IBT will give you a little bit of safety during any power or even for some of your peak loads. Evaporative condensers, liquid ammonia pumping system, chilled water pump automation, and sorry, there is a small mistake. It should be IE3 or IE4 motors and automation of the complete plant. And apart from that, what are the new innovations and challenges? we can think of low charge ammonia refrigeration system. Also, you can also think for the air conditioning of the dairy also can be done by using ammonia chilled water. We are doing in many process halls, we are using chilled water. And CO2 refrigeration system, of course, it may take more time. That is for some value-added products. You want to keep it in a cold room, you can use CO2 systems also. So I think I've come to the conclusion of my thank you. Thank you once again, ISHRE and REFCOLD India, for giving me the opportunity. And thank you, Shruti. I'm open to any questions from the audience. If any questions are there, I'm willing to take. Thank you.
Thank you so much, sir, for such an insightful session. I believe today our audience has been able to, grasp from your experience over the decades the technological enhancement that has happened in the field of refrigeration. And definitely we had, a learning curve when it came to energy efficient refrigeration and refrigeration of basically the new era paradigm. And on this note, I would like to inquire from you that when it comes to energy efficient refrigeration, what is the constraint that's holding us in opting for a CO2 based? Because you mentioned that in innovation, and there is a lot of life cycle assessment. There is a lot of EIA happening these days. So how?
See, there are two disadvantages because India being a tropical climate. Am I audible? Hello? I'm audible?
Yes, sir.
Yeah, basically, we are in a tropical climate. So what happens is the CO2 pressures are little high in our ambient conditions. Say, for example, at 4 or 5 degree temperature, the CO2 pressure goes up to 40 kgs or 50 kgs. So your designing of the system is more critical. CO2 systems are mostly used abroad for negative temperatures, like for your ice cream store or a butter store you can use. You can use CO2 system for a what you call standalone cold rooms or a standalone cold storage where you have about say 10,000 pallets, 5,000 pallets of a butter or an ice cream. You can use, but it will come to India. But the major factor is one is the design part because of the high pressures involved, and the other thing is the cost. The technology which is coming from abroad is expensive, so you need to indigenize lot of things, and it may take some more time to come into the CO2 refrigeration system.
Sir, thank you. And yet another question I would like to inquire that with the new emerging trend of the health consciousness or amongst the youngsters, while they are conscious about their diet, their intake, so the changing pattern of the dairy consumption, dairy products that are being consumed by the youngsters, that is the predominant population of India these days. Going to affect the type of refrigeration methodologies that we opt for in long run?
No, I think, see, you basically now a lot of byproducts of milk is coming. Like I would say in this COVID pandemic, the last 6-7 months, the milk and milk byproduct sales have increased. Rather, people have started using more milk byproducts, drinking flavored milk, cheese eating, or butter, using butter, and even lot of other things which are byproducts. Even people nowadays, you don't find people you doing curd in your homes. They are using a lot of curd purchased from the shops, and these curds are all manufactured, and so these all require a lot of refrigeration. But at the same time, you have to be cost competitive. So you have to be energy efficient in your refrigeration system. And similarly, you have to also market and also tell the advantages of using a milk and milk byproduct. One of the biggest available protein is milk. So it is very good for all the youth. That's the reason Amul has come up with a lot of ads, and a lot of ads are coming up. So it is Only thing is you have to be competitive enough to compete with the other drinks which are available. So you have to be energy efficient.
Refrigeration once defined India altogether a different country with diversity. I believe that today changing trends on refrigeration have helped you define how you preserve your milk. So on that note, I would like to thank Sudhir sir for his time and his valuable insight regarding the refrigeration industry. And also, I would like to enlighten all of you that if you have a query, you may mail to him at sudhir@flickmail.com, which is his official ID. And we would now lead on to our next session. Thank you, ladies and gentlemen.
Thank you once again.
Hello, good evening. Welcome one and all once again. I would like to wholeheartedly welcome the participants who have joined the session just now. We are on the last session of the day and have a dome of industry experts with us. It is my pleasure to welcome Mr. Ramesh Prajanpe to you all. He would enlighten us about the pressure vessel design when it comes to refrigeration. And I would like to give you all a brief introduction about his profile. He's the proprietor at ARTI. He is MTech from IIT Mumbai. Before starting as an independent consultant, he has served with Kirloskar Pneumatic, Carrier Refrigeration, and Voltas Air International. He's a fellow of ASHRAE and he has also received the 50-year Distinguished Award from the organization. He's a fellow at Institution of Engineer, and he has published more than 75 papers in international journals. He has been the past president of ISHRAE Pune chapter and ASHRAE Western India chapter. Over to you, sir. Please enlighten us with your experience and your audience.
Okay, now I'll start my presentation. You can see all of you can see my screen. Okay,
yes, sir,
you can
screen
hear
is visible.
me? You can hear me?
Yes, sir, we can hear you.
Okay, now I'm starting my presentation. This presentation is, I would say, is a continuation of 7 presentations which I made in the month of July and August for ISHRAE. I've presented 7 sessions on ammonia refrigeration, and I would say this is the 8th presentation as a continuation of that. This is a presentation of ammonia pressure vessels used in ammonia refrigeration systems. Now, which are the pressure vessels which are used? We should look at it carefully. The main vessels which are used is an oil separator after the compressor and before the condenser. This is important item because it separates out the oil from and does not allow oil to go into the system. The second important vessel which is in the refrigeration plant is high pressure liquid ammonia receiver. This ammonia receiver is for accumulating the entire charge of refrigerant into a system. The third item is interstage cooler, which are of different types. One is open type interstage cooler and one is closed type interstage cooler. So these 2 coolers are important depending upon the system design. The next is surge drum and low pressure ammonia LP vessel. This is LP vessel is used only in case of force feed ammonia circulation systems and not in gravity flooded systems. Next item is surge drum mounted on a shell and tube flooded chiller. The next item is accumulator for gravity flooded systems as against LP vessel, which is atom number 5. So this is used in gravity flooded systems. The next atom is knockout drum to protect the compressor from the liquid. And the last atom, last vessel in a system is an oil pot for oil draining. Now we need to understand the difference between the surge drum, accumulator, knockout drum. Many people, 90% engineers or operators, consider that all these three vessels are same, but they have different functions. When we come to that, we will talk about it. Now the next slide. Now I'll go to the next slide. Okay. Now, when we design these refrigeration systems and the vessels, we follow certain standards. I am now defining all the standards which are used for designing of these vessels. These are the standards. The first one is ANSI, that is American National Standards Institute, stroke IIR. IIR means International Institute of Ammonia Refrigeration. This is a safety standard for design of equipment. The next important standard, I am very happy to inform you that up till now in India there was no standard available, but we have designed AR1 standard, and I am also happy to inform you that Bureau of Indian Standards has accepted it, and it is under printing by BIS as a government standard. So it will become compulsory for mandatory for all ammonia plants, and the quality of ammonia plants will improve substantially. The next standard is ANSI ASHRAE 15 standard, which is a safety standard for refrigeration system. Then the most important standard is ASME B31.5, which is for design standard for refrigeration vessels and heat exchangers. And ASME section 8 is a fabrication standard, how to fabricate the pressure vessels. So these are the important standards. The next standard, sixth standard, is TEMA standard, that is Tubular Exchanger Manufacturers Association, is also a standard which we refer many times. In our AR1 standard, we have taken references of all these standards, and I would say that as a chairman of that committee, the standard has come out very well, and it will be useful to Indian engineers. The next standard is ISO, International Standards Organization for Boiler and Pressure Vessels requirement. Then EN 378 for design, construction of testing requirements. IS 660 standard is a safety code for mechanical refrigeration, is an Indian standard. Then the OSHA standard, occupational safety and health hazard, which is again a reference with ANSI ASHRAE 15. And the last one is IS 2825. Now it is being modified as IS 14430 as a closed circuit ammonia refrigeration system for code of practice for unfired pressure vessels. So these are the various standards I wanted to give you. I'm going to put all this my presentation on the website, so anyone who wants to further look at it can have a reference of it. There is no need for anyone to take it down anything. Kindly concentrate on what I am speaking and what I am showing. Now our design standard, AR standard, what we have taken is we have taken the pressures as 21 kg for the water cooled applications and 27 kg for air cooled application. These are the pressures which are different, because whatever standards I showed you earlier are based on European conditions where the ambient conditions are low. So their design pressures are different. In India, being a tropical country, our ambient temperatures go as high as 40 degrees centigrade, whereas their design standards are all for 35 degrees centigrade maximum dryable temperature. So we have considered these higher pressures, and therefore our systems will become more safer. The ideal alternative as per European standards, as an alternative they give, consider design pressure at 17 degrees uh, above uh, above minimum dryable temperature, and for water cooled application, and 17 degrees centigrade above dry bulb temperature for air cooled application. So water cooled go water temperature, that is wet bulb, plus 17 degrees centigrade, and for air cooled applications, whatever your city's maximum dry bulb temperature, add 17 degrees in that and consider the design reference. This is my comment, fifth one. I would prefer designing both high side and low side vessels for the same pressures. This will allow you to reduce ammonia charge. Ammonia can be then stored in LP vessel in the plant room, and uh, then you need not pump down the system. The next is design precautions. What are the fabrication standards? Use of boiler quality plates IS 2825 or 14430 or IS 2002 grade 2A is very, very important, or SA 516 grade 570. Most of the Indian manufacturers today, ammonia plants, to save the cost, use IS 2062. IS 2062 is a structural quality steel and is not meant for uh, pressure vessels, and therefore a lot of accidents take place. The cracking takes place because IS 2062 plates have higher carbon content, and my sincere request is don't use it. Use boiler quality plates, and this is covered in our AAR standard. Use proper thickness of plate as per TEMA standard, Tubular Exchanges Manufacturers Association. There are three considerations. Consider joint efficiency as 0.7 if you are not going to do any radiography test. Add corrosion allowance because of the weather corrosion, the thickness goes on reducing. So you need to add 1.6 mm corrosion allowance to the thickness. Fabrication as per ISO 16528 section division 1 or EC European standard, these standards. All these details will be available to you. You need not take down any details at this stage. Now, how to calculate the pressure vessel thickness? Many plants which I have visited, when I asked people what thickness material you have used, oh, they said to be on the safer side, we have used 16 mm plate, 20 mm plate. It is not required. Do not waste national uh, hardware or national raw material. Use the correct thickness and correct quality of plate. Quality of plate is more important than thickness. And the calculation of thickness, I am just giving you a sample calculation. Let us say a vessel size of 30-inch diameter, 12 feet long. The formula is thickness equal to pressure into inside radius. Here the inside radius is 15 inches. Down below, S into E. S is the allowable stress for whatever material you are using. SA1516 has a stress of 17,500 pounds per square inch allowable stress, and E is the joint efficiency. So when you take 0.7, when there is no radiography, that is DP test only, dye penetration test, then 0.85 if you use 10% radiography, or if you use 100% radiography, then it is joint efficiency is 1. As the radiography percentage goes up, your thickness of the vessel will go down and you will save in the cost of the vessel. So this is the thickness calculation. The thickness for the vessel 30-inch dia 20 feet long is 300 P into 15, that is inner radius, into bracket 17,500 S, that is strength, joint efficiency 0.7. So the thickness comes to 9.47 millimeter. Add corrosion allowance of 1.6 millimeter. So thickness required becomes 11.07. Now you don't get a plate of 11.07. So use the next available plate, of 12 mm thickness. So this is a calculation I am giving. You should calculate your thickness and use the correct grade. Now, but for the sake of easier understanding, for normal sizes of receivers, what we use is 24-inch, 13-inch, 36-inch, 42-inch, 48-inch, and I have given the ready reckoner thickness calculations: 10 millimeter for dish end, 10 millimeter for plate, 30 inches 12 millimeter, 36 inches 14 millimeters, 42 inches 16 millimeters, and 48 inches 18 millimeters. So this is a ready reckoner. You need not calculate. You can use this straight away, which I have calculated. Now, welding of heat exchangers, pressure vessels is very, very important. I have seen many plants where, to save the cost, people use many joints, 3, 4 different plates, and they are welded together. Kindly do not do that. Try to use a single plate of longer width as much as possible so that your welding is reduced. Up to 20 inches, 24 inches, you can in fact use seamless pipe instead of using rolled steel plate. But when you are doing the welding, the root run, the basic run, the first run should be used with tungsten inert gas, that is argon. This prevents the black carbon formation inside the vessel and does not contaminate your system. The root run could be teak, argon, or MIG. MIG is metal inert gas for vessels. Welding should be done by qualified welder, certified level minimum 3, and most important, no use using good quality plate and good quality of welding methods. It is essential to use good quality welding rods also. The welding rod should be used AWS A18. Don't use 6013. Lot of people use 6013, which is a structural welding rod and not pressure vessel welding rod. So remove, when you are welding the vessel, remove valve internals, otherwise the gaskets and o-rings will get damaged, strainers, solenoid valve coils, etc., because we do not want these items to get damaged when you are doing the welding of the heat pressure vessels. The next, now we will go to individual pressure vessels. We have seen now how to calculate the design thickness of the pressure vessels, how to use correct welding rods, how to use correct material. Now we go to the individual vessels. The oil separator, the first vessel is oil separator, which is used for uh, separating ammonia and oil, because ammonia and mineral oils are not miscible with each other like your CFC, HFC gases, where the oil is mixed and is carried in the system. In ammonia plants, oil is immiscible. So oil separator is required primarily for lubrication of compressor and not anywhere else in the system. So it is essential that we must keep oil into a closed loop of compressor and oil separator, and therefore efficiency of oil separator is very, very important, so that oil is drained from the various, instead of from various points in the system. It can be only controlled within a closed loop of compressor, oil separator, that's all. So installing efficient oil separator even at higher cost is therefore strongly recommended, so that minimum oil is contained in the closed loop compressor loop and system remains free from oil. Because as you all agree, it is the refrigerant which does the cooling, and oil has no cooling effect. So if your oil is there in the system, your efficiency of the system will drop. So try to keep oil into the system bare minimum. Try to control it with a good oil separator. These are the different oil separators which are of various different efficiencies. This is an oil separator where the oil coming from compressor through the pipe is distributed into a vessel, and those vessels has those pipes. Through those pipes there are small holes, so oil falls down. Oil is a heavier density than ammonia, so oil settles down below, and gas is sucked back. Gas goes to the compressor. The float valve is there, so when the oil level increases, the float valve opens the sump and returns the oil back to the compressor. So this is the function of an oil separator. This is first type of oil separator. This is the standard oil separator which is available currently with our Kirloskar compressors. This is an oil separator which has only a baffle plate. If you see, when the refrigerant enters, the it strikes the baffle plate and heavy density oil droplets drop down. There is a change of direction for the mixture, and the gas goes out. This oil separator is not very efficient. It is about 65 to 70% efficiency. So 23% oil goes into the system. I would suggest that in this there is a second design which is available, which I will show you. This slide shows how to calculate the oil separator diameter and the length. But these calculations I am not reading now for the paucity of time. These will be available to all of you. You can calculate your own sizes of the oil separator. The second oil separator, which is more efficient, is if you see there is a demister pad inside the oil separator. So the demister pad is a stainless steel pad and which traps the oil. The oil falls down, liquid droplets coalesce and drop down, and only vapor is sucked by the compressor. So this is more efficient oil separator, and I would recommend that you use this kind of oil separator than only a gravity separation oil separator. The third oil separator is also is very efficient, is 85 to 94% efficient. There is stainless steel demister pad, as you can see, which is built into inside the oil separator. This design is available in India. The next design is a spiral oil separator. The oil and ammonia refrigerant moves into a spiral, and in the process, the heavy air density oil falls down and the gas goes to the compressor. These are the various types. The the most efficient oil separator, if you ask me, is used in screw compressors. Why screw compressors use very high efficiency oil separator? Because the compressor is totally flooded with oil. Unlike reciprocating compressor, screw compressors are fully, the rotors, male and female rotors are immersed totally in oil, and therefore there is a lot of oil inside the compressor, and therefore you will see any screw compressor the biggest component into the system compared to reciprocating compressors. So you need very high efficiency oil separators so that minimum oil goes into the system. If you look at this diagram, there is a two-stage oil separation. One is compressor discharge, in which heavy density oil falls down. Then there is a baffle, and then this remaining low gas with low oil content goes through the coalescing filters. There are filters, two filters, if you can see, through which the ammonia, oil, and gas travels, and most of the oil is recovered, and the discharge vapor is practically free of oil. I would say in air compressors, when we use these kind of oil separators, the air is so much free of oil that we call it a breathing quality air. So a person can breathe that air. So you can imagine how efficient is the oil separator. So these efficiencies, but as you know, as the efficiency goes up, the cost will go up. But it is one-time investment, and your oil draining problems from the system will be reduced. The next vessel we come to high pressure ammonia receiver. The purpose of high pressure ammonia receiver is to store the entire charge of the refrigeration system. If you want to do any repairs anywhere inside the system, you pump down the entire quantity of ammonia gas and take it into an oil separator. So this vessel is also very, very important, and it is high pressure ammonia. So it is the high pressure, same pressure as the condenser pressure, or 21 kg, or the working pressure is normally 13, 14, 15, maximum 15 kg per centimeter square gauge under Indian conditions. This oil separator, if you see, has an oil pot, because the oil, whatever is escaping from the oil separator, comes to the system, and we need to further remove that oil from the system. So there is an oil pot which is again for removal of oil, and these are the various nozzles on the oil separator, on the receiver, and also there is a gauge glass. This gauge glass indicates that how much ammonia or refrigerant you can store inside the receiver. The recommended practice is 75 to 85%. Why I'm saying this? Kindly remember that liquid is non-expandable or non-contractable. If you fill up the entire receiver with the liquid ammonia, when the ambient temperature will go up, the liquid will tend to expand. And if there is no space provided into the receiver for expansion, the vessel will burst. Therefore, maximum allowable quantity to be stored is 75, 80, maximum 85% when the entire system is pumped down. This is very, very important. So what are the precautions to be taken? Selection to be done on the based on assumption that it should be able to accommodate entire charge of refrigeration system. This is, as I mentioned, if somebody wants to do the repair, one should be able to pump down the entire charge. The receiver should be selected 80 to 85%. Many times a standby receiver is provided as per the requirement, so that you can keep the plant in operation. If it is a critical plant, you cannot stop the plant. So you can pump down the ammonia into the second receiver and continue to use that side when you are attending the one side of one ammonia receiver for some thickness measurement of dye penetration test or any other test. These are the important locations of the nozzles which are to be fitted onto the ammonia vessel. A is the liquid inlet, B is the purge connection. If you can see, the purge coupling is, try to keep the purge connection as away from the liquid inlet as possible, because liquid inlet has a mixture of ammonia vapor and ammonia liquid when it comes into the receiver, and we do not want ammonia to be wasted in purge line. So purge connection should be as much as away as possible. There is a relief valve, that is pressure relief valve on the vessel, which is normally used as a dual pressure valve. Equalizer connection, if you are using two ammonia receivers, then the pressure in both the receivers need to be equalized. So there is a gas equalizing line and a liquid equalizing line. There are two connections for pressure equalizing. Then there is a liquid outlet and level column, level indicating gauge glass. The next item, as I show you, the purge connection for the receiver, as I mentioned, keep it away as much as possible, because inlet has a cloud of pure gas, and we don't want, if the gas connection, purge connection is too near to the liquid inlet, it may waste your ammonia gas. So keep it as away as possible. These are the various sizes of receivers. How much is the weight of the receiver? What is the internal volume? How much ammonia quantity it can accommodate? And etc. etc. This charge will be available. HR20 110 means 20-inch diameter, 110 inches length, and these are the various sizes I've given up to 96 inches. You can use, select the ammonia based on your quantity of ammonia, pounds of ammonia, which is 85% full on this vessel. The next vessel, important point, as I mentioned, means receiver should be located well below the condenser level so that liquid will fall or go to the receiver by gravity. This is important because the condenser pressure and receiver pressure is same. Do not keep receiver next to your condenser. I have to modify my personal experience. Lot of ammonia plants where, especially with evaporative condensers, people tend to keep it next to the ammonia, next to the condenser, and then your liquid will not get drained into the receiver. It will accumulate in the condenser. It will affect the condenser performance. In one of the plants, I had to literally lower down the receiver, and there was no space into the plant room, so I had to hang it from the ceiling level by fixing a bracket to get a distance between condenser outlet to receiver inlet. This should be about, in my opinion, at least 1.5 to 2 feet between the condenser outlet to receiver inlet. The oil drain pot I have already talked to you. There is a liquid level gauge glass. Purge point should be as away as possible. Inspection of receiver must be done once in a year to ensure that the thickness of the shell as well as descents has not deteriorated. This you need not empty the receiver. Now the thickness sensors gauges are available and you can measure the thickness when the vessel is in operation. Use only dual safety valve without a stop valve below. Most of the people use stop valve because the dual safety valve is of not good quality, and when I ask them why you are using this valve, they say, oh, the safety valve leaks. And therefore, to prevent, now there is no point in having a safety valve when you have a stop valve below. 90% plants, if you see, still they use stop valve below the safety valve, which is a wrong practice, not recommended by the standards. But if you at all want to use stop valve, many customers insist, no, 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 we want to use stop valve. Then do one thing, keep the valve fully open, remove the handle, and that handle should be kept under lock and key with the manager so that nobody by accidentally closes this valve. So this is also protect the receiver directly from sun rays, rainwater, etc. If you are keeping the receiver outdoor, many people keep the receiver outdoor near the evaporative condenser on the terrace or outside the machine room in the plant room. The next important vessel we come to is interstage cooler. These interstage coolers are used only in case of two-stage refrigeration plants, not for single-stage refrigeration plant, because the low pressure gas from the discharge of the low pressure goes into the interstage, and then it is cooled down, the superheat is removed, and then the gas is compressed into a high stage. There are two types of interstage coolers. Open type interstage cooler, which is a very, very efficient, most efficient interstage cooler. So interstage coolers, as I mentioned, are required for two-stage ammonia plants, and the LP vessel outlet should be installed above the inlet. When you are using open interstage cooler, This is a very important point because interstage pressure is very low, and your LP vessel, low pressure vessel, is also having a very low pressure, maybe operating at minus 40 degrees centigrade, and the interstage pressure is corresponding to 1.6, 1.8 degrees centigrade, which is about 1.2 kg, 1.1 kg. So the difference between the pressure is very low, and it takes time to fill up the LP vessel many times because there is a pressure drop from the line coming out from LP vessel to the incoming of LP vessel and outgoing of interstage cooler. So in this line, to avoid the pressure drop, allow it to flow by gravity, and therefore this interstage cooler needs to be installed above the level of the LP vessel, which normally becomes then 13 or 14 or 15 feet high, and many plant rooms are designed for 10 feet high machine room. Then this vessel has to be kept outside the plant room. LP vessel and interstage cooler has to be kept outside the plant room. So when you are designing a new plant, ensure if you are using interstage open cooler, design the plant room for 15 to 20 feet plant room height. These are this is the most efficient interstage cooler, but difficult to handle it, difficult to operate it also. So I would say, although the efficiency is high, this is a selection of the cooler, how to select the cooler based on the velocity, based on the number of cylinders, etc. I will not read this for the paucity of time, but my presentation will be having these calculations. This is the construction of open interstage cooler. You can see in the green line the gas inlet and the liquid gas out and the gas outlet, and the liquid connection. You can see both liquid inlet and liquid outlet on the left hand view, that is liquid inlet and liquid outlet. Here in this vessel the mixture, both the high stage gas and the low stage gas gets mixed and come to the interstage pressure, and therefore there is no coil inside this cooler, and therefore the interstage pressure is the most efficient pressure, and you get best efficiency with this kind of coolers. There is a perforated dotted line plate also to distribute the gas uniformly. This is the internal construction. I would recommend go in for a new plant. 90% people now I'm using, after using few customers with interstage cooler, they are not able to operate the plant. The operator creates a problem, the compressor breakdown takes place. So most safer side is to use closed interstage cooler with a coil, because inside the coil there is a high pressure liquid then, and therefore there is no problem. You can mount the cooler inside the machine room. It need not be mounted at a height. You need not have an automatic capacity controller, which is very essential in open interstage cooler operation, to ensure that the interstage pressure does not exceed the allowable pressure. And it is, as I mentioned, it is not as efficient as open interstage cooler. But the construction of the cold interstage cooler, these are the calculations, and this is the construction. There is, if you see inside the cooler, there is a coil. So this gas comes down and it is the gas is inside the coil. Gas is outside the coil. Inside the coil there is a liquid ammonia, and liquid ammonia cools down and reduces the superheat of the gas, and the with less superheat gas, then it's sucked by the high stage of the compressor. So this is closed interstage cooler with subcooling coil, and I would recommend use this as much as possible. Now we go to the most important vessel, low pressure. low temperature ammonia vessel. There is a full session can be conducted only on the design of this LP vessel, but we will take some important points of LP vessel. This is an LP vessel, ammonia pump circulation vessel. There are two pumps, if you see, one pump working, one pump standby, and this LP vessel is a low pressure vessel. It is, I would give you an example, simple example. It is like a corporation water tank. So long as corporation water tank is full of water, you will be ensured that you get enough water in your houses. Similarly, the LP tank, LP vessel ensures that when there is a liquid ammonia of a particular height, 40-50% height, and at minus 40 degrees centigrade, your ammonia refrigeration system is okay. There is no problem. This LP vessel helps us to separate out the system into two components. One is refrigeration system and one is your process system. Process system in which liquid ammonia is used as a utility. The process could be IQF, or it could be blast freezer, it could be plate freezer, it could be air coolers, anything. And you circulate liquid ammonia of a required temperature through these vessels. The liquid ammonia comes down. The liquid ammonia circulated normally is about 4 to 5 times the actual evaporation taking place. So the mixture of liquid and a little bit of gas, one gas and 3 or 4 times liquid returns back to the LP vessel, and then only the pure gas is sucked by the compressor. The compressor is then do not get any liquid stroke. It is free, only ammonia gas which is sucked by the compressor. So these LP systems are very important, very popular, and they are used in most of the ammonia plants which are low temperature below minus 20 degrees centigrade, and large capacity plants where there are many air coolers or uh, uh, the process side equipment like blast freezer, IQFs, etc. is much away, about 50 meters, 60 meters from the plant room. So if you use gravity cooling, then the suction gas will get superheated. Therefore, it is recommended to use LP vessel, because LP vessel is kept inside the machine room in a closed loop refrigeration system. As I mentioned, there can be an independent lecture of 1 hour only on LP vessel design. These are the LP vessels. This is the LP vessel construction. There are important points. Is there is a liquid channel inside, if you see, where liquid, returning liquid, wet return comes down, and there is a vortex breaker. Why vortex breaker? Because if you see, even in your household applications, when your basin, wash basin gets filled up with water, and if you suddenly remove the stopper, you will find the vortex formation. To avoid similar vortex formation, there is a vortex breaker which is very essential. Otherwise, bubbles will be formed, and those bubbles will enter into your ammonia pump, and your system will have a lot of problems. So this vortex breaker is important. I will not go into the details, more details of this design. As I mentioned, we can have independent lecture on only ammonia pump circulation systems, which are delivered in Germany, in Nuremberg, for the German engineers, and it is available on my website. If you visit my website, you will find my lecture on pump circulation systems. So these are the low pressure vessel details. Important consideration: liquid collection channel is very necessary so that no liquid enters to the compressor. Vortex breaker essential. Location of inlet and outlet connection should be as apart as possible. Gauge glass or standpipe is required. Insulation of vessel pumps mounting vessels is essential. Bypass line for pump is required. Use of flow regulating valves instead of hand expansion valves is recommended. Oil pot location is important. Selection of diameter and length to accommodate surge volume. What happens when your plant stops suddenly? The liquid into the air coolers will flow back to your LP vessel, and LP vessel should be able to accommodate this surge volume, and therefore the diameter selection of LP vessel is very important. The maximum liquid level to be provided is 35 to 40%, not more than that. The next slide, this is a complete, whenever I trained that LP vessel along with the pump sets and all the valves, the gauge glass, the controls, etc., so that you will have no problem. Nowhere there will be an error of installation taking place. So this is the LP vessel. Next we go to the surge drum. Now remember, as I mentioned, there is a difference between surge drum, knockout drum, and the LP vessel or the accumulator. The surge vessel, as the name suggests, is meant only for gas. There should be no liquid into the surge drum. It is used for shell and tube flooded chillers. The important point, if you see, the surge drum is mounted on the shell and tube chilled water or a chilled brine chiller, and these three pipes, if you see the green line, very important. I will give you an example. In Ahmedabad, I visited one plant where people said that if they use 6-cylinder compressors of the compressor, it's a 9-cylinder compressor, no liquid comes to the compressor. But if you use 9 cylinders, there is a liquid stroke. Now we need to change the diameter of the surge drum, which is a wrong theory. What is required, just try to understand the theory. The liquid droplets are heavier than the gas and they will tend to fall down. So on the liquid droplet, there are two forces. One is gravity pull down and the second is compressor pulling. If the compressor pulling is higher, the liquid will enter the compressor. If the gravity force is higher, the liquid will fall down. And therefore, instead of increasing the surge drum size, if you just add more number of pipes between the surge drum and the vessel, then your velocity will fall down and the liquid ammonia will fall down into the chiller by gravity. No gas liquid will enter into the compressor suction. So very important to use more number of pipes than a single pipe. People use single pipe and then they use, the velocity is very high. Try to maintain the velocity of ammonia around 75 feet per minute, not higher than that. So this surge drum is important. Remember, surge drum is pure gas. There is no liquid into the surge drum. Therefore, it is called, this is the surge drum fabricator. You can see 1, 2, 3, 5 pipes. Now, this design is from Germany. People have not used this because they love to use more number of pipes. It is because of the, which I just now explained to you. So designing of chiller with surge drum is an important aspect. Important considerations I have mentioned you. I will not go into the more details of this because we are already coming to the uh, end of our session. Accumulator for gravity flooded cold storage. This is, if you ask me, one of the most difficult uh, design of the accumulator. The accumulator has both liquid as well as gas. a flooded ammonia operation, nor not for pump circulation systems. Wherever you are using gravity flooded system, the accumulators are used. And this is an accumulator which is where to locate the accumulator, what should be the height of the accumulator, etc., is a separate subject which needs, as I mentioned, another lot of discussion. This is an air cooler with an accumulator. If you ask accumulator manufacturer or a air cooler manufacturer, he normally avoids giving the accumulator. He says, no, accumulator design is a system designer's responsibility. My responsibility is to give the air cooler. So accumulator design is very, very important. And as I show you this slide, there is a PHE, plate heat exchanger, and the accumulator. The accumulator is mounted so that there is a liquid. The PHE is full of liquid. Lot of people fill up the vessels only up to 80%, and then they say that, oh, we are afraid no liquid should come to the compressor, so we maintain our evaporator levels to 85%, which is wrong. Evaporator should be fully flooded and the level should be controlled into an accumulator. 85% evaporator liquid level will give you only 85% efficiency of the evaporator. So fully flooded evaporator is a must, and accumulator location, accumulator diameter, accumulator sizing is an important calculation. So to avoid all these problems, Alpha Level, their PHE, if you see, they give along with the accumulator with a U-turn accumulator. And I've used this U-turn accumulator in many places, and it has given me satisfactory service. So this U-turn accumulator is available only with Alpha Level. This is their patented design for the PHE, ammonia PHEs. This is an accumulator design. This is a ice bank system with the accumulator, and this is accumulator selection, as I mentioned, accumulator sizing. Now we come to the next vessel, which is knockout vessel, knockout drum. Knockout drum is a protection vessel. It is not compulsory into the system. If you design the system well, there is no need to have knockout drum. But wherever you are having problems in the system, liquid coming to the compressor, insert a knockout drum. A knockout drum is inserted between the evaporator outlet and the compressor suction. It is kept into the machine room. So the liquid which is coming out along with the gas does not enter the compressor. It goes first into the knockout drum. Only then the gas is sucked by the compressor and the liquid is kept inside the uh, knockout drum. There is a demister pad also to eliminate liquid going to the compressor, and this is an important vessel. Uh, in case of accidents, I don't use a knockout drum in any of my plants because my accumulator or my LP vessel is properly designed. But this is, I am giving you a suggestion. This vessel, use it in by the plant operators or the designers who are facing the problem of a liquid coming to the compressor. This is a knockout drum, and this is knockout design basics. I will not go. And the last vessel before we end into our presentation is a oil pot. A oil pot is used in a LP vessel system, low pressure vessel system, pump circulation system. An oil pot accumulates the oil and it separates out from the evaporators, and then only oil refrigerant vapors are sucked. The oil is collected into the oil pot. I would recommend, instead of draining oil from various points into the system, like oil separators, like condensers, like your air coolers, like your accumulators. Instead of that, provide a single oil pot into the entire plant room where all the oil is collected from various points. Don't drain the oil from each point. Provide a pipeline and take it into an oil pot so that all oil is collected into the oil pot, and you can then drain the oil from the oil pot. The advantage of oil pot is you don't have to drain oil from various points which can lead to accidents, because if you open the oil drain valve suddenly the ammonia oil and this will come out, and the operator, if he by accident opens the valve much more, then he runs away, and then the valve remains open, and then there are ammonia accidents. So instead of that, use oil pot. Or another point, to prevent this sudden opening of a drain valve which is on each component, use hand operated pressure relief valve, which is when you press the handle, then only the valve opens. If you release your hand, the valve closes. Automatic shut off drain valves are available, and I use those valves on my system. So this is one of the last valves, last point which I wanted to show you. Our time is up to 6 o'clock, 5 to 6. I am very particular in observing our time limits so that I don't encroach upon the time of some other lecturer who is eager to make his presentations. I trust I have been able to give you the various uh, vessels which are used into ammonia systems or various refrigeration systems. These LP vessels are used also in CFC, HFC plants. Accumulators are also used in CFC, HFC plants. So this will be useful to those people who are using CFC, HFC plants. And I'm sure this presentation ISRE will put on the website, and it will be available to all of you. I always believe in sharing my all the knowledge and all the information so that everybody is benefited, and uh, this is a very wrong knowledge which many consultants prefer. They don't share their knowledge. They feel that their knowledge will go down. It doesn't happen. I haven't seen that by sharing my knowledge my business has gone down. In fact, people have much more confidence in me that whatever I am designing is with their knowledge. Many refrigeration plants I see, when I ask them for the drawings, when I ask them the piping drawings, the design details, they say, oh, the consultant has not provided us anything, which is, in my opinion, is incorrect practice. I don't want to comment on other consultants, but this is my suggestion, and I would share whenever I get the opportunity of all on my points. With this, I thank REFCOLD organizers for giving me an opportunity of this sharing my knowledge for 1 hour. Thank you very much. With this, I would end my presentation, and I hope you all of you liked it. I have given my Gmail number, I have given my cell number, I have given my web page details. So all these details will be available to you. If you have any questions, please send me a mail, and I will definitely, I guarantee that I will reply to you. Thank you very much, and I end my presentation. I hand over back to the organizers. Thank you.
Thank you so much, sir, for your valuable time and insightful presentation. It really means a lot. Ladies and gentlemen, please take a note of sir's email address and his respective phone number. Make sure that you follow up with him over mails for your queries, and they will certainly be addressed. Thank you so much, sir, for being a part of ISHRE, ASHRE, and across various platforms over the pandemic. You've been sharing a lot of knowledge, and over the past 50 years, you've been contributing so much to the industry. We are really overwhelmed to have you on the platform today and to be able to host you, sir. Thank you so much for your valuable presence.
Thank you,
And
and
on that,
best of luck to all of you. Thank you.
Thank you, sir. And on that note, I would now request all of you that this is the end of today's session, but there's an array of interesting presentations that is waiting for you tomorrow. And I would look forward to your all presence in the coming session, which is tomorrow, which would be our last day for REFCOLD. And in lieu of the same, I would also like to inform you that if you have not visited our exhibition halls, then you are missing out on a lot, ladies and gentlemen. So today we'll be winding up the session. And on this note, I'd be requesting you to please take a leap forward and visit the exhibition halls and see what's there to interest you.